let us invite Professor Dr. Harish Parthasarathy to please come on the stage. We look forward to your insights and guidance, sir. A very big round of applause for sir. Sir, please come.
Energy of E alpha for the Hamiltonian edge. The edge acting on psi alpha is E alpha multiplied by psi alpha. H is the Hamiltonian operator, like Schrodinger's equation, in which Hamiltonian becomes minus h square by 2m into del square plus a potential, or you can have a vector potential minus h square by 2m del plus IEA by h square plus E minus EV. So these are examples of Hamiltonians which tell you how the wave function evolves. For example, if you have an atom, you have a wave function, and the wave function evolves after applying an electromagnetic field to it. You can change the state. It can make a transition from one energy state to the other energy state. Or if it was initially in a superposition of stationary states, you get a superposition of stationary states with coefficients depending on time. Now, if it is in this state with E alpha, and then the probability of it having the energy E alpha is e power minus E alpha by kT, according to the laws of thermodynamics. So if you normalize it by dividing the partition function, you call these probabilities as P alpha, then the mixed state becomes P alpha, psi alpha, psi alpha. So in such a state, if you calculate the average value of an observable, in quantum mechanics, the average value of an observable in a pure state is psi alpha x psi alpha. So in terms of coordinate systems, you can say, see, observables in quantum mechanics are non-commuting operators. They are matrix kernels. So in terms of wave functions, you can write this as psi alpha x star x xy into psi alpha y dx dy. So this can be looked upon as a matrix, a continuous matrix acting on a wave function. Then you put a transpose conjugate to get the average value of x in the state psi alpha. But originally the probability of psi alpha occurring is P alpha. So you can write the average value of x in the state rho, mixed state rho, as P alpha, psi alpha x psi alpha. But this can also be written as trace of summation P alpha, psi alpha into x. Because trace of AB is trace of BA. If you take a ket vector and bring it to this side, it becomes a bra vector. So trace AB is trace of BA. So the average value of the observable in the state rho is trace of rho x. This is a classical quantum mechanical formula for the average value of the observable x in the state rho. Okay, in the case of state f pure state x, what is the meaning of average value of x in the state psi? You know that this is equal to psi x star xxy psi y dx dy. So what does this mean? If you diagonalize x, so you write it as summation lambda alpha E alpha over alpha, where E alphas form an orthogonal basis for the Hilbert space. Then the possible outcomes, the values that you measure of x are the eigenvalues of x, namely lambda alphas, and the corresponding E alphas are eigenvectors. So you have the orthonormality relation between eigenvectors, says that this is delta alpha beta. It's equivalent to saying that if you act on this side by a ket, you can look upon a ket vector as a column vector and a bra vector as a row vector. So if you act both sides by E beta, what do you get? You get x E beta is equal to lambda beta E beta. So if you measure x and you find that the eigenvalue that you get is lambda alpha, then the state collapses to the state E alpha after the measurement. This is one of the biggest problems in quantum mechanics, which makes it a wrong theory in practice, that you cannot give physical meaning to the reality of the quantum state. What reality you can give, what real meaning you can give is to the value of the measurement made by the observer. You have to connect the quantum mechanical system with an observer who is taking measurements. And when an observer makes a measurement, the state collapses. So after that, the state evolves from the collapsed state. That is the biggest problem in quantum mechanics. You cannot have objective reality. If another observer comes and takes a measurement, another state will collapse to another state, and then it will evolve from that state onwards. So is there, when you observe a tree, you say, okay, the tree is here. Somebody else observes the tree, he says, yeah, the tree is looking in this way. But is there something, a third observer says, okay, no, the tree is looking this way, in this way. But is there any objective reality to the meaning you can attach to a tree? No, you cannot. Because you have to shine a signal on the tree and then measure that signal and then say, okay, this is what the tree looks like. So if there is no observer, there will be no tree. That's the fundamental problem in quantum mechanics, that without introducing an observer, you cannot give meaning to reality. So I have written a book on this. I'll maybe mail it to you after it appears in the publication. So now, if you want to look at the average value of x, the average value of x can be written as, in the state, say rho, can be written as probability of getting the eigenvalue lambda alpha multiplied by lambda alpha and summed over alpha. But what is the probability of getting lambda alpha in the state rho? If it is in the state rho, then the probability of getting lambda alpha is trace rho alpha, this, which is psi alpha rho psi alpha. That multiplied by lambda alpha. So average value in the state of x in the state rho is summation lambda alpha psi alpha x psi alpha. It can also be written as trace of summation lambda alpha psi alpha into x, which is equal to trace of, psi alpha, so rho, which can also be written as trace of rho into x by the spectral theorem. So all routes lead to this thing. This formalism of quantum mechanics was first developed by Paul Dirac in order to unify the two pictures of quantum mechanics, wave mechanics and matrix mechanics. Wave mechanics due to Schrödinger and matrix mechanics due to Heisenberg. Now let us go back to the original problem. Let us go back to the original problem of QKD. So Alice is in the state rho, Bob is in a state rho, and the eavesdropper is in a state rho. So this is the original state of the system, A, B, C. Now Alice wants to communicate a message to Bob without Eve being able to eavesdrop. How does she communicate? She takes a measurement on her state. She takes a measurement on her state and reports the value of the measurement, that she outcome measurement, to Bob. And then accordingly Bob will apply a gate to his sister and try to determine the state which Alice wanted to send. So this is what is called the classic problem of teleportation. Teleportation using entanglement. I thought I will first discuss these issues and then come back to the filtering problem. That will be more complicated. So in teleportation, what happens is that in the teleportation, Alice has a state, let us say rho A tilde, which she wants to send. Say rho A tilde, which she wants to transmit it. She will club this. See, if Alice makes any measurement on her state, it is not going to affect the state of Bob or Eve, because they are disentangled. What is a measurement? A measurement is, let us say, a PVM. Let us say PVM less than alpha less than n. PVM means projective valued measurement. So what is meant by projective valued measurement? P alpha square is P alpha. It's a projection. P alpha, P beta is 0. If alpha is not equal to beta, they are orthogonal. And P alpha is a Hermitian operator. So this is called a projective valued measurement. For example, if x is an observable and you decompose x spectrally into its eigenspaces, then you have these are all one projection valued operators, rank 1 projection valued operators. So these form a system of measurement. When you measure this P alpha, then the outcome you get is the eigenvalue of this. How do you decide that? So you simply take P alpha x P alpha, use the fact that these are orthogonal, and you get simply lambda alpha P alpha. So if you look at the probability of getting, if you, no, it should be this way. Rho, let's say rho is the state of the system. No, x is the observable. You measure this, then what do you get? You get lambda alpha. And what is the probability of getting this? You can, if rho is the state of the system, and you measure P alpha, you get P alpha. So the state of the system collapses to this. So if say the state of the system is summation, say P alpha, psi alpha, and I apply P alpha rho P alpha to this, I get simply P alpha, psi alpha, which is P alpha. And if you take the trace of this, P alpha rho P alpha, if you take this, since this is a one-dimensional projection, its trace is 1. So this is P alpha. So the concept of measurement in quantum mechanics and wave collapse is the following. It can be summarized in this way, that if the state of the system is rho and you measure P alpha, then the probability of getting that P alpha is trace rho P alpha, and following the measurement the state of the system collapses to P alpha rho P alpha divided by a trace of the numerator. This is rho alpha. So now if you take a measurement but don't measure the outcome, then what is the overall state of the system? It is nothing but the probability of getting the state rho alpha multiplied by state rho alpha, which can be written as summation P alpha rho P alpha summed over alpha. And you see this is the collapse state. So this collapse state can be also written as summation P alpha P alpha. Can be written as P alpha like this. Now if you have an observable X and you decompose it spectrally, say into, let us say, E alpha like this, and then you have a state rho. So what is the probability of getting lambda alpha? Probability of getting alpha in this state is trace rho E alpha. This is the probability of getting the value lambda alpha in this state. And what is the average value of X? It is simply lambda alpha into this probability, which is trace of rho E alpha. It can also be written as trace of rho times summation lambda alpha E alpha, which is trace of rho X. Right, this is the basic postulate. Then you come to dynamics. Okay, now we have seen that Alice cannot influence the other states. It's in an disentangled state, rho C0. Suppose Alice makes a measurement on her state. So P alpha, rho A 0 P alpha, her state will collapse to this. But the state of Bob is not going to get changed by this. So rho B 0 tensor rho C 0. This is divided by trace of rho A 0 into P alpha. So no matter what she measures on her state is not going to send Bob, so Alice cannot communicate anything to Bob. It's called a separable state wherein you cannot communicate. In an entangled state, on the other hand, you don't have this sort of a state. What you have is that the joint state of A, B, C at time 0 is of the form summation, say P alpha, say some C alpha, or let us write it as rho A alpha tensor rho B alpha tensor rho C alpha summed over alpha. These will be states. It's called an entangled state. Now when Alice makes a measurement on her state, inevitably Bob's state and Eve's state will also get affected. How do you see that? Suppose she makes a measurement, say using a PVM, say P beta, using a PVM P beta on her state. Then what does this collapse to? It collapses to P beta, rho A alpha, P beta, tensor rho B alpha, tensor rho C alpha. And then she takes a trace on her state. Of course, you have to divide it by trace of rho A alpha into P beta, summed over alpha. Now what does Bob do? Bob is going to compute his own state. How does he compute his state? He takes a partial trace over Alice's state and Eve's state. So the partial trace operation is the crucial one here. If rho ABC is a joint state, then the state of A alone is simply given by trace over BC of trace rho ABC, and the state of B alone is given by trace over AC of rho ABC, and the state of C alone is given by trace over AB of ABC. So it is this partial trace which transfers the information from Alice to Bob. Right? So you see this state has become modified by beta. So I can write the overall state as rho A, it depends on both alpha and beta. Alpha was the original index and beta was a measurement made into trace rho B alpha tensor rho C alpha. Now you take a partial trace over A and C to get the state of Bob. This is rho B. What does it come out to be? It comes out to be equal to trace of rho A alpha beta multiplied by trace of rho C alpha multiplied by rho B alpha summed over alpha. Now obviously this is not going to be equal to 1 because rho A alpha need not be a state. It will depend on beta in general. So it means Bob's state will also depend on beta. That is the idea behind entanglement. Many people don't confuse this idea of entanglement. They don't see it in a very general perspective. So I thought I should make this more clear. Suppose you take an entangled pure state. Entangled pure state. Say just you have two parties A and B. So the overall state is psi A alpha, psi B beta. By this I mean this is nothing but the tensor product of two states. So psi A alpha tensor psi B beta. This is the initial state. Call this as psi of A and B. Now Alice makes a measurement on her state. It can be a PVM or a POVM or anything. So what is the overall state? It is given by, first you convert it into a mixed form, psi. Then you make a measurement. Let us say M beta tensor I. Alice measures her own state. It's a PVM, so root PMI. Here you put root M beta into I. So the overall state of Alice and Bob now is this one. Because Alice is making this measurement on her state. And then you divide it, to normalize it, you are taking this divided by the trace of the above, which is root M beta into this into I. So it becomes M beta tensor I in psi. And then Bob takes a trace over Alice and Eve's state to get his state. So you are going to trace over 1 and 3, Alice and C, to get the state of Bob. This is the state of Bob, which I call it as rho B. And obviously this will depend on beta. It won't be independent of beta. Okay, that is the way you can transmit information. Now let us go to, okay, now once you are through with this, you can ask what is the effect of noise on this transmission. Here so far we have not brought into effect any noise. So the channel adds noise to the system. How does it add noise? It is through what is called a TP-CP map. Noise in quantum communication. So TP-CP map. What is the meaning of TP-CP map? Okay, you start with the state rho, you apply a unitary evolution. It's like Schrodinger's equation, in which you have the rate of change of the state at time t is equal to minus I h comma rho. Or in the case of pure states, d by dt of psi t is minus I h into psi t. If you convert this into mixed state form, it becomes a commutator. Because you can take a mixed state as psi t, and you take d by dt of this. So d by dt of this is equal to I d by dt of psi t multiplied by psi t plus psi t multiplied by I d by dt of psi t. So here it will act to the left, here it will act to right, there will be a conjugate, you will get h comma rho. H comma rho means h rho minus rho h. This is what is dynamics. Now the joint state, so after time t the solution to this is equal to, you can write the solution to this as psi t is e power minus I t h into psi 0. But this is a unitary operator which is ut. H is a Hamiltonian operator which is a Hermitian operator, and e power minus I t times a Hermitian operator is a unitary operator. So the solution to this equation is simply given by rho t is e power minus I t h rho 0 e power I t h, or equivalent to ut rho 0 ut star. Now this is a conservative operation because unitarity preserves the probability. Unitary operators have satisfy the property that u dagger is u inverse, or u dagger u is 1, or u dagger is 1. So it will preserve the total probability. It's a conservative process. But now suppose I choose one Hamiltonian with probability P1, another Hamiltonian with probability P2. There is an uncertainty in what Hamiltonian you are choosing to operate. For example, signals are being transmitted through the channel. Each time you transmit, the ions are in a different configuration. They generate different potentials. So you can look upon the ions as generating a random potential. So H becomes a random Hamiltonian operator. Then noise is introduced. So you choose the unitary operator UK with probability Pk, and you sum over K. So this becomes T acting on rho. This is a noisy channel. It preserves the trace. Total probability is 1 because UK dagger UK is identity, and trace of rho is 1, and summation Pk is 1. So obviously you have the relation that trace of T rho is equal to trace of rho, which is 1. It's a positive map. It takes positive operators to positive operators. So the TP-CP map is the most general form of a quantum noisy operator. Now the question is, how do you recover? How do you recover the original state from the transmitted state, from the noise corrupted state? Now in classical Shannon theory, you know that there are methods to do so based on coding. That if you transmit information at a rate less than the capacity, then there is a coding scheme, although it doesn't say how to design the coding scheme, but there exists a coding scheme by which you can design a receiver which, if you encode asymptotically long sequences into sequences, then you can transmit in such a way that the error probability of detection converges to zero, provided you transmit at a rate lesser than the Shannon capacity of the channel. And if say nu y given x is the transition probability of the channel, then your source is px. So your source probability is px, and nu is the transition probability of the channel. Then you compute the entropy of y given x, and you compute first the uncertainty in x, and then you compute the uncertainty in x given that y has been received. This is same as hy minus hy given x by an identity, and this can be written as h of the output. So h of q minus h of nu, or you can also write it as where qy is given by summation of px into nu y given x. That is the probability of the output getting the symbol y, and x is the source. X varies over the source alphabet, and h nu is nothing but minus summation px nu y given x into ln nu y given x, summed over y and x. So it can also, h nu can also be written, h y given x can also be written as h nu, which is summation of px hy given x is equal to x. So what is the meaning of this? Initially you have an uncertainty hx about x. After you receive the symbol, after you receive the signal y, the remaining uncertainty about the source is hx given y. If you subtract these two, this tells you how much uncertainty you have removed by transmitting the information. So this is the net amount of information that the source has transmitted to the receiver. Alice has transmitted to Bob. So I write this as mutual information xy. And what is the maximum information you can transmit? You maximize over all possible source distributions px. That is called the Shannon capacity. Shannon's classical coding theorem, which is not a very difficult theorem in probability theory, tells you that if you transmit at a rate less than c, what do you mean by saying transmit at a rate less than c? So let us give some meaning to it. You take, say, r messages, or 2 power nr messages you take. Let us say I take 2 power nr messages, call them as w1, w2, etc., w 2 power nr. And I encode them into bits of length n. I encode them into bits of length n, bit strings of length n. So for example, w1 becomes, say xn w1, which is equal to, say, xw1, x2 w1, etc., xn w1. Like that I encode all these messages into bit strings and transmit all these bit strings over the channel using the transition probability y given x. Then you have a detection scheme to assign with each of these possible received code words a message in such a way that the error probability will converge to zero, provided that r is smaller than c. That means you can transmit at the most, of course c is what? C is given by maximum over px of hy minus hy given x. So if you transmit, if your rate of transmission is smaller than this, then you can recover with zero error probability. What is the version what is the quantum mechanical version of this? Let us look at it. Quantum mechanical version gives you a higher capacity and tells you how to get rid of noise provided you transmit, how to design a coding scheme. First, let us look at the problem of removing noise from a channel. So rho goes to T rho. Now suppose the range of rho belongs to a subspace C of the Hilbert space. And suppose T is generated by noise operators coming from a noise manifold N. That means T acting on rho can be written as in this way: Ek rho Ek dagger. Ek dagger summed over K. Just as it's a generalization of summation Pk UK row, UK dagger, a noisy Schrodinger channel in which each Hamiltonian you are selecting with different problem. You can write it in this form. And since trace of row is 1, you can bring this to this side and write it as trace of row times summation EK dagger EK is 1. Or equivalently EK dagger EK for the summation K is 1. Identity. So this is called a TP-CP map. This is the noisy channel. Now I want to know, and these EKs are the noise operators. So EKs come from the noise manifold N. So you can choose any set of noisy operators from this manifold of operators on the Hilbert space. Now these noise operators form a subspace of the space of bounded operators on the Hilbert space. So suppose you transmit it using this, and suppose these N satisfy the condition, namely let PEC be equal to P, the projection onto the code space. C is a subspace of H and PC is the projection on the code subspace. And suppose P times N2 dagger N1 P is equal to, is proportional to P. So this is of the form lambda of N2 dagger N1 into P for all N1 N2 belonging to N. Then we say that the nil Leflame conditions are satisfied by these noise operators and the code subspace operators. This is called the conditions for the Lil-Leflame theorem. If the conditions of the Lil-Leflame theorem are satisfied, then the theorem says that there exists a recovery map by which you can recover from T row row. That means you can apply RK acting on T row RK dagger, summed over K, and get back row for some recovery operators. Now, irrespective of what the state row is, provided row has subspace, has range within this subspace C. This is called the celebrated Nil-Leflame theorem. Nil-Leflame theorem. So, this is how you recover. Instead of Alice and Bob, which I had mentioned earlier, what we are doing here is you are having a ABC. It's an entangled state. How do you generate an entangled state? Row A0, tensor row B0, tensor row C0. And then A generates his electromagnetic field, B generates his electromagnetic field, C generates his electromagnetic field. The three electromagnetic fields are acting in different Hilbert spaces. But then the total energy of the field is what? A's electromagnetic field, electric field, plus B's electric field, plus C's electric field, and square. Similarly, magnetic field will be B's magnetic field plus, A's magnetic field plus B's magnetic field plus C magnetic field square. Total energy is D3x. If you take the total Hamiltonian, this is called the Hamiltonian, you can write it as EA square plus EB square plus EC square plus BA square plus BB square plus BC square plus 2 EA dot EB to 2 EA dot EC plus 2 EB dot DC. So you have interaction terms. So the Hamiltonian of this whole system can be written as Hamiltonian of A plus the Hamiltonian of B plus the Hamiltonian of C plus the interaction Hamiltonian between AB plus the interaction Hamiltonian between BC plus the interaction Hamiltonian with AC. Now this will not generate entanglement. This will not generate entanglement. This will not. But these terms will generate entanglement. So if I call this total thing as H and I put the unitary operator as UT, then the total state becomes UT dagger. So now this becomes an entangled state. So now if Alice makes any measurement on her state and Bob tries to measure what has happened, then immediately it will affect Bob and he can recover. In other words, Alice will try to send an alphabet, say from A. So she will take X and she will encode that X into row A0 in the form of row A0X. And then we will go here. Bob, if Bob will do what? Bob will look at his state by taking trace over A and C. And this will be simply equal to trace of row B. It will depend on X. And it will also depend on time T. So in effect, Alice has encoded a state. Alice has encoded a classical alphabet X into a state which Bob has received. So X belonging to the alphabet of A is encoded into row BX. Another way to do is Alice can encode her state into row AX, transmit it over the channel, and Bob receives the state row BX, which is T acting on row AX. So this is called CQ channel. This is called the CQ channel. CQ means classical quantum. Why is it classical quantum? Classical is the alphabet which Alice wants to send, and quantum is the state into which the alphabet has been encoded. Okay. So I want to prove the theorem. It's there in my book, but it was first proved by Holebo and Winter. This is a classical generalization, quantum generalization of the classical Shannon theorem, which says the following. Suppose Alice encodes this into rho x and transmits this to Bob. Then let us say x appears with a probability px. Then what is the effective average state of Bob? Average state of Bob is this. Okay. And what is the entropy in the state? That is hy. Px rho x. This is hy. And what is x? X is Alice. So what is hx? Hx is nothing. But what is hy given x? Hy given x. First, what is hy given x is equal to x? That is nothing but the entropy of rho x. And what is the average value of this over all x? This multiplied by that is hy given x. Right? That is nothing but summation px summed over x. Okay. Now what is the information transmitted by Alice to Bob? It is hy minus hy given x. Okay. This is ixy. As in the classical case, this is h of y, which is summation px rho x minus summation over x px h rho x. Okay, how do you compute entropy in quantum mechanics? That is of course a different story. In classical information theory, you compute the entropy of a source as minus summation px log px. Why do you use this formula for the entropy? One, if all the px's are equally probable, you get maximum entropy. When there is maximum uncertainty, you get maximum information when anything has occurred.